Picture yourself training a massive neural network. You have millions of parameters, noisy gradients from mini batches, and a loss surface that twists and turns in ways nobody fully understands. The question that has haunted machine learning for decades is deceptively simple. How big a step should you take, and in what direction, on each update? Pick a learning rate too large, and you bounce around chaotically. Pick one too small, and training crawls. And the right answer often differs from parameter to parameter, from layer to layer, and from one phase of training to another. This paper, by Kingma and Jimmy Barr, introduces Adam, an optimizer that became the default workhorse for training deep neural networks across the field. To understand why Adam mattered, it helps to remember what came before. Plain stochastic gradient descent takes a step proportional to the gradient, scaled by a single global learning rate. It works, but it treats every parameter identically and is sensitive to how gradients are scaled. Then came AdaGrad, which gave each parameter its own learning rate by dividing the update by the square root of the sum of all past squared gradients. This was brilliant for sparse problems, like text models where rare words show up occasionally and need bigger updates when they do. But AdaGrad has a fatal flaw for long training runs. That accumulated sum only grows, so effective learning rates monotonically shrink towards zero, eventually stalling progress. RMSProp, an unpublished method from Jeff Hinton's Coursera lectures, fixed this by replacing the running sum with an exponential moving average of squared gradients, so old information gradually fades. RMSProp worked beautifully in practice for non-stationary problems, but lacked theoretical grounding and had quirks around initialization. Adam, whose name comes from adaptive moment estimation, elegantly combines these ideas and adds two crucial twists. The algorithm maintains two exponential moving averages for each parameter. The first tracks the mean of the gradient, which is essentially momentum. The second tracks the mean of the squared gradient, which captures how large and variable the gradient has been recently. Think of these as estimates of the first and second moments of the gradient distribution. The update rule then divides the smoothed gradient by the square root of the smoothed squared gradient, scaled by a global learning rate. Intuitively, you're moving in the direction of recent gradients, but normalizing by how noisy or large those gradients have been. So parameters with consistently small gradients still get meaningful updates, while parameters with wildly varying gradients get damped. The first crucial twist is bias correction. Both moving averages start at zero, which biases them towards zero in the early steps of training, especially when the decay rates are close to 1, which they typically are. Imagine you're trying to estimate someone's average height by starting your running average at 0 and slowly mixing in new measurements. For the first several measurements, your estimate will be way too low. Adam fixes this by dividing each moment estimate by 1 minus the decay rate raised to the power of the current time step, which exactly undoes the initialization bias and gives you a proper estimate from the very first step. This sounds like a small detail, but it turns out to matter enormously in practice, particularly when the second moment decay rate is close to 1. The second beautiful property is the effective step size. Because the update is the ratio of the first moment to the square root of the second moment, the magnitude of each parameter update is roughly bounded by the global learning rate. The signal-to-noise ratio is built right in. When recent gradients have been consistent, the numerator is large relative to the denominator, and you take a confident step. When gradients have been noisy, or you're near an optimum where gradients fluctuate around 0, the ratio shrinks and steps become smaller. This gives you automatic annealing as training progresses, without anyone having to design a learning rate schedule. It also makes the update invariant to the scale of the gradient. So if you multiplied all your gradients by 100, Adam would produce nearly identical updates. This trust region interpretation, where the step size sets an upper bound on movement in parameter space, makes Adam refreshingly easy to tune. On the theoretical side, The authors prove a regret bound in the online convex optimization framework, showing that Adam's regret grows like the square root of the number of time steps, which matches the best-known rates for this setting. The bound becomes especially favorable when gradients are sparse, similar to AdaGrad's known guarantees. The proof requires a decaying first moment coefficient and assumes bounded gradients and parameters, standard assumptions in this literature. Empirically, the authors test Adam on logistic regression on MNIST and on IMDb movie reviews with bag of words features, on multilayer perceptrons with dropout, and on convolutional networks for CIFAR 10. Across these settings, Adam matches or beats SGD with Nesterov momentum, AdaGrad, RMSProp, AdaDelta, and the quasi-Newton SFO method, often converging considerably faster in wall clock time while using minimal memory. The paper also introduces a variant called AdaMax, which replaces the second moment, an L2 norm of past gradients, with an L infinity norm, essentially tracking the maximum absolute gradient seen recently with exponential decay. This update has even cleaner properties, with no bias correction needed for the denominator, and tends to be more numerically stable in some settings. The authors also mention temporal averaging of parameters as a simple add-on for better generalization. Now, looking at this with the benefit of hindsight, Adam is not without its issues, though many of these were only discovered later. The proof in the original paper contained an error that subsequent work corrected, and Adam can fail to converge on certain convex problems where SGD succeeds. The adaptive learning rates can hurt generalization in some domains, particularly computer vision, which is why SGD with momentum still dominates in some image classification benchmarks. The epsilon in the denominator, ostensibly just a numerical safety net, sometimes ends up playing a meaningful role in the dynamics. And the interaction between Adam and weight decay turned out to be subtle, leading to the later Adam W variant that decoupled them properly. Despite all this, the core algorithm has proven remarkably durable and remains a default choice for training transformers and most modern architectures. Now let's walk through some questions you might have after hearing all of this. Why does dividing by the square root of the second moment estimate work so well as a per-parameter learning rate? The intuition is that the square root of the second moment is essentially the typical magnitude of the gradient for that parameter. So when you divide, you're normalizing each parameter's update to roughly unit scale, which means parameters with tiny gradients still get meaningful updates, and parameters with huge gradients don't blow up. It's like z-scoring your steps. This is why Adam is scale invariant. Multiplying gradients by any constant leaves the ratio essentially unchanged. What exactly does the bias correction fix, and why does it matter most early in training? When you initialize the moving averages at 0 and use decay rates like 0.999, your estimates are heavily weighted toward that 0 initialization for many steps. Without correction, the second moment estimate would be much smaller than the true squared gradient early on, which would make the denominator artificially small and your steps artificially huge, potentially causing divergence. The correction term, dividing by 1 minus the decay rate to the power of the time step, exactly compensates for the missing weight and gives you an unbiased estimate from step 1. After many steps, the correction approaches 1 and becomes irrelevant. How is Adam different from just doing momentum and RMSProp together? It's close to that, but with two key distinctions. First, Adam applies momentum to the raw gradient rather than to the rescaled gradient, which changes the dynamics subtly. Second, Adam includes the bias correction terms that RMSProp lacks. Without that correction, using a second moment decay rate close to 1, which you need for sparse gradients, would produce enormous initial steps and frequent divergence. So Adam is more than the sum of those parts. The bias correction is what makes it robust across a much wider range of hyperparameters. For large-scale recommendation systems, Adam's contributions are especially relevant in a few concrete ways. Recommender models like two-tower retrieval networks or deep ranking models often have massive embedding tables, where some item or user IDs appear in millions of training examples, while long-tail IDs appear only a handful of times. This is exactly the sparse gradient regime where per-parameter adaptive learning rates shine. Rare embeddings get meaningful updates when they do see gradient signal, instead of being washed out by a global learning rate tuned for common features. Adam, and especially its sparse-friendly variants, are workhorses in production training pipelines for exactly this reason. Beyond that, the trust region property of Adam, where step magnitudes are bounded by the learning rate hyperparameter, makes it much easier to ship updates to large ranking models without unexpected blowups. When you're retraining a model nightly on petabytes of new interaction logs, you want optimization that's robust across non-stationary data distributions, since user behavior shifts, new content arrives, and seasonality matters. Adam's exponential moving averages naturally adapt to these shifts in a way that AdaGrad's monotonically growing accumulator cannot. The lesson many practitioners eventually learned, though, is that for the dense layers of large ranking models, switching to AdamW or carefully tuning the epsilon and decay parameters often unlocks meaningful additional quality. So understanding Adam's mechanics deeply, not just using it as a black box, pays real dividends at scale.